Okay, I want to explain the concept of the action dimension of a group, which is, well, we'll see what it is. So suppose I have a group, and for today I'm going to assume that it's of type F, which means that it's K pi 1, it's KG1, is homotopy equivalent to a finite complex. And then I'm going to say the geometric dimension of G is the smallest dimension of any CW complex, which is a model for its K pi 1. And the action dimension of G is the smallest dimension of a manifold model for its K pi 1. KG1. So you might think it's another way that you can say this is if you can thicken this CW complex up to a manifold, then you can take its universal cover, which will be a contractible manifold. So this can also be described as the smallest dimension of a contractible manifold, which you can act freely. And have some sort of obvious, the geometric dimension of G is always clearly less than the action dimension of G. And in fact, on the general principles, this is less than 2 times the geometric dimension of G. Because any CW complex up to homotopy can be thickened to one of twice the dimension. It can be thickened to a manifold of twice the dimension.
So your manifold can have boundaries?
Yes. In fact, that will be important. And most of the time they will have boundary. And maybe I'll also point out this is an equality if start with a K pi 1 manifold, a closed manifold. So this action dimension was studied by Besvina, Kapovich, and Kleiner in a 2002 paper. Their main goal was to show that when you had a case where the group was given by God, where the group acted on a manifold that was given by God, that you could prove that that was in fact the smallest dimension that it acted on. So they introduced this idea of the obstructor dimension, which I'll write OD, eventually write O, obstructor dimension of G. And it's defined this way. First of all, there's maybe a classical notion of an obstructor. So they say a finite complex K, this is a finite CW complex, is an M obstructor if the classical Van Kampen obstruction from 1933 for embedding it in Rn, obstruction for embedding in Rm is non-zero. So this is, in their paper, they give a very interesting description of this. I'm not going to say much about it. I'll just say that it's one definition is there's a certain Z2 cohomology class in the configuration space of 2 points of K. That sort of counts the self-intersection of K. So,
So in particular, it doesn't embed in RA.
in particular, it doesn't embed in Rm, right? So, the classical Van Kampen example would be if you had a non-planar graph, its a one obstructor. It's a two obstructor, yeah. In fact, that will come up in a second. So then these guys wrote, I want to define what this means. K with quotes around it is contained in the boundary of G. So the formal the definition of this is this means that there exists a coarse embedding from the cone of infinite radius on K. Well, usually I think of this into the universal cover of some BG. Maybe this is but in fact, really you could just say that this is defined on the zero skeleton of the cone. So this means,
So that's just the Euclidean cone?
this just means the Euclidean, you take the ray across K and divide K cross 0. Just smash K cross 0 to a point. And coarse embedding is like the quasi-isometric embedding, except the control functions it just has to be bigger than some instead of linear functions in the almost Lipschitz conditions, you just replace them with functions going to infinity. So it's weaker than quasi-isometric. And then the expected fact that you get here is that if you're in a situation where the group, so they write it, this is a lemma in Vesvina, Yakovich, and Kleiner, if G has a boundary, then it's pretty obvious that this weaker condition holds. So, for example, if G is a hyperbolic or cat zero group, it has a boundary, and if K is a subcomplex of its boundary, then you get an embedding of the cone on K. Or, in fact, if G acts on a space EG that has a Z-set compactification, then that's enough for this. But in fact, we don't really need this. And then their definition of the obstructor dimension of G, well, it's going to be 2 more than the largest possible M here. It's 2 plus, I wrote the minimum, but I should have said maximum. The maximum of M such that K is an M obstructor and K is contained in the boundary of G. So this was with quotes around it. So the idea for this is that if G acted on a contractible manifold, a good contractible manifold, then if G acted on a contractible manifold, then you expect the boundary of G to be contained in the boundary of this contractible manifold, which is, say, some sphere. So this M is an obstructor for K, and hence for a boundary G to be contained in here. And so, so if this is realized by some M, this says that G does not act on contractible M plus 1 manifolds, so the smallest it could act on would be M plus 2.
Yeah, but M is not closed, so.
M is not closed, right? So
does it live inside a?
but it's still,
It's
I mean,
universal cover
just think of
inside.
its interior is still an open contractible manifold, and the sort of the boundary at infinity should be Sn minus 1.
Okay.
So let me just do the simplest example and then say, so maybe the simplest example is where G is equal to, say, the product of two free groups, or more generally, the same argument is going to work with, it's the product of D copies of a free group of rank 2, on two generators, or D plus 1. So in this case, the classifying space for F2 is a wedge of two circles. So for the product of these two things, you have the product of the wedge of two circles. So the geometric dimension is 2. On the other hand, the only way you can think of it making this act on a manifold is to thicken these both up to surfaces, and then you get it acting on R4. And in fact, that is the answer. The obstruction, maybe I should have said. So the main theorem of Svina-Kaplowitz and Kleiner is that the action dimension is always bigger than or equal to the obstruction dimension. And usually it's equal. So usually this is a way to figure out what the action dimension is. So the reason to see that the obstruction dimension here.
So this argument was kind of a cartoon proof of this
Yeah.
result? Okay.
Yeah. Right, you have to do it with embedding, with this coarse embedding of the cone. So the obstruction dimension is 4, and here's the reason in this case. Well, the boundary of a free group is a Cantor set, so it contains 3 points. So the boundary of the free group across the free group contains 3 points joining 3 points, which is the utilities graph, which doesn't embed in, which is 2 obstructors, we just said, so the minimum embedding is 4. And in fact, I think Van Kampen's original complexes, which didn't embed in R, twice the dimension plus 1, were iterated joins at 3 points. So the same argument shows that the action dimension of this is as large as possible, which is 2D plus 2. Now, Svina and the natural things that they wanted to do with this, they did. Namely, if G is other examples are if G is a lattice in a semi-simple Lie group, then the action dimension is what you expect. It's the dimension of the, so this is mainly interesting when it's a non-uniform lattice. It's the dimension of the symmetric space. And they also, the student of Svina also did the mapping class group, whereas the action dimension is the dimension of the typonal space. Now, okay, maybe I should have said my collaborators, but maybe now's the time. So here's, actually, okay, so I have a couple papers on this. First of all, there's a paper with Grigory, Avramidi, Davis, Oken, and Schreve, which is figuring out determining the action dimension for right-angled Artin groups. And then there's my student Zhang Lei's thesis, together with a paper I wrote with Jingyan Huang. So this has come out now in the bulletin of the AMS, which does this for general Artin groups, at least if the K-pi1 conjecture is true for them. And what I've been working on now for a while, I'm writing a long paper with some combination of these with Giang, myself, and Kevin Schreve, and we're trying to do sort of the general construction for what simple complexes of groups. Although, so this one is in process of being written, and this one is, no, both, this is in the bulletin of the LMS, and that one will be too.
It's a simple complex of groups.
Yeah, right. I'm going to explain that. So this is in Artin and Hepler. I'm just taking the terminology from them. A simple complex of groups. So this means that you have a poset Q, and you have a functor from Q. It has to be actually just the diagrams have to commute on the nose. A functor from Q to the category of groups and monomorphisms. So that means basically that that you have a collection of groups indexed by the elements of Q, and you have monomorphisms when one is less than the other. What plays the role of the fundamental group of this complex of groups is if at least if the geometric realization of Q is simply connected, then I'm going to let G. So this simple complex of groups, I'll write G of Q, and I'll write G just to be the direct limit of this system, which is basically the group that this determines. Now, in fact, all I'm going to talk about today is in the case where this poset is the poset of simplices in some simplicial complex. So in fact, at least in today, and in fact, I basically just have, okay, maybe I'll say that now. So today, Q will be, I'll use the notation S of L. So L will be a simplicial complex, finite simplicial complex, and this will be the poset of simplices, including the empty simplex. At some stage, I need to talk about not including the empty simplex, and I'll call that S0L. So the empty set, this pointing out the empty set is an element here. Yeah.
So there's one group per cell of the complex, and
Yeah.
like, basically the group includes the one.
Yeah, in fact, it's sort of the reverse way it would work for trees. The bigger the cell, the bigger the group. Okay. It's not like in trees where the vertex groups are the biggest. Here, the bigger cells have. Oh yeah. Okay. So the first thing what we're going to do is you can paste together. You can get a realization of this data, namely. You can paste these things together. What you do is, at least in this case, you take these BG, one for each cell sigma, and you cross it with what's called the dual cone. You take the cone on the length of sigma. I call this the dual cone. It would be the dual cell if it was a if this was a sphere, take the disjoint union of those, and then you glue them up in some obvious manner. And that's how, this gives you the information for obtaining, so Bryson and Heffler call this the aspherical realization of this simple complex of groups. It's a poset of spaces where the posets are these k pi 1s. What's not clear is what Ruth and I did in a minute for, there's the k pi 1 question, is, the question is when you paste these small k pi 1s together, do you end up with a k pi 1? And, well, it's pretty easy to see this as the right fundamental group, but the question is Bg of SL equal, in other words, is its universal cover contractible? For anything I do, I'm going to need this to be true. Okay, so I'm going to call this, right, or the k pi 1 question has a positive solution. So in fact, the place this was raised was in a paper. First place this was raised, a paper I wrote with Ruth Charney over 20 years ago. So let me define one example of this. This is what I call, so I'm going to do two examples. This is going to be one of them. It's what I call the Artin complex. And the other is going to be called the graph product complex. So here I start with a Coxeter system. The complex L is the nerve, what I call the nerve of the Coxeter system, which means its vertex set is S, and a subset of S corresponds to a simplex if and only if it generates a finite Coxeter group. So this says that these are the spherical, this says S is the vertex set, and sigma contained in S is a simplex if and only if the corresponding group is finite. Okay, and then the Artin group corresponding to this, so it has generators, I call them X sub S, and its relations are the braid relations, which says that the alternating product of X sub S and X sub T is the same thing in the other order. So there's M sub ST factors here, where M sub ST is the order of ST in the Coxeter group. These are the braid relations. Okay. And maybe the last thing I'll mention is that the complex, what I'm going to call the Artin complex is I'm going to define these. I'm going to look at these A subs, the Artin group, meaning the group generated by these X sub S in sigma, and so this is going to be called if sigma is one of these spherical sets in the nerve of S, this is going to be called a spherical Artin group, or an Artin group of finite type. And so my Artin complex A S of L is the obvious thing. It's the set of these A sub sigma. Poset of those. Ruth and I considered this actually, and I mean the Lean proved that each of these things has a nice model as a hyperplane complemented by a manifold, and it's not known whether the k pi 1 conjecture problem is always positive for that, but it is, for example, if L happens to be a Flag complex. or in many cases, and Ruth and I proved that when it was positive, we proved that it was, well, we raised the question of when it was, we proved that in certain cases that it did have a positive solution. In which case it meant that the Artin group had a nice K-pi one. That's by what I just said. So my plan is, the other example I plan to do is, I plan to just do one other example, state the result, and then say something about how the methods that you use to do this. So the second example is what I call the graph product complex. Maybe I should have said the case of right-angled Artin groups is just this case where all these MSTs are 2 or infinity. So all these relations just read x of s, x of t equals x of t, x of s. So this is also, so here the situation is this. I'm going to start with a simplicial graph, which then I can complete to a simplicial complex called the associated flag complex, which, or the clique complex. It means you just fill in a simplex for each complete subgraph. And now, what do I mean by the graph product? So I have some, so again, I'll let S be the set of vertices. I have some collection of, I have some collection of groups, and then every time basically I'm going to make 2 of these, well, let me just say, I'm going to define G to be what's called the graph product over this graph, the one skeleton of L, of these G sub S's. And it's defined the same way you define a right-angled Artin group. You take the free product of the G sub S's and you divide by the normal subgroup generated by making G sub S and G sub T commute whenever S and T are an edge. Whenever ST is an edge. So when you do this, when each of these is infinite cyclic, this is what you mean by a right-angled Artin group. And here we're going to look at, again, we're going to look at the simplices in the flag complex. The simplices correspond to complete subgraphs. So if sigma is in this flag complex, you get, let's say we'll write G sub sigma will just mean the ordinary product. Every 2 things are connected by an edge, so we'll just get the ordinary product of these G sub S's. And in that case, the direct limit of these things is this, and so well, okay, so maybe I'll just say this. So in this case, starting with the K pi 1 question does have a positive answer as long as this L is the flag complex. So in this case, I can glue together these BG sigmas, and I get something whose universal cover is contractible. And the group that acts on it is this G. Okay. So these are the 2 cases I want to compute the action dimension in. Okay, so let me just say what the answer is first. So, I mean, one interesting thing about it is that, is that the answer in both of these cases is, I think, is interesting, and it comes out to depend on L. So, so here's the theorem for Artin groups. So A is the Artin group, and I need to suppose, which might always be true, that the K pi 1 problem has a positive solution. Then the answer is that if, and L is this nerve of the Coxeter group, which I'm going to call its dimension D. It's a D-dimensional complex. So the first thing is that if the top homology of this in its dimension is not 0, that implies that the action dimension of A is the same as the obstruction dimension, and which is as large as possible, which is basically 2 times the geometric dimension. Geometric, like in the right angle case, the geometric dimension is just the dimension of this plus 1. And, well, the second thing, it depends which version I'm talking about, but, okay, so I'll write the second thing is what happens when this is 0. So, in fact, we have a slight weakening of this, slight strengthening of this. It says that if L embeds, so this is what's in Giang thesis. It says that if L embeds in a contractible complex of the same dimension, so in this paper I've taken to abbreviating that EDCA, I don't know why, equidimensionally contractibly embeddable or something. Then the action dimension is in fact of A is in fact 1 less than this. It's less than that. So so actually, what we in the paper I wrote with the other 3 guys, Avermindi, Oken, and Schreve, the version of this for Artin groups, for RAGs, is as the following. We just proved that if the top homology is equal to 0, then the same conclusion. Now, why are these related? How do you get a complex to embed in a contractible complex? Well, you just want to add cells to make it contractible. So, if you kill some homology, you have to increase something in the next highest dimension. So if this is not 0, you can't kill it without introducing D plus 1 dimensional homology. And in general, you see that to be able to add cells and not produce anything above dimension D, you need that the top homology is 0 and the D minus first homology is free abelian, something like that. Doesn't have torsion in it. So this is not as bad as it sounds. It's just a slight weakening of this condition. Now okay, I still have a lot of time. I'm doing better than expected. So the theorem for graph products and here there's a difference. So maybe I should just set up some notation. So here there's a difference between whether it's a fundamental group of, so I'm going to let, say, G, let's think about the case where this is a graph product complex. So basically, and let me let, I'm going to switch to calling them V's, the vertex, instead of S, but maybe I'll, well, my notes I call them V, so V is the vertex set of L. And so let's let M sub V be a manifold of an aspherical manifold of minimal dimension. An aspherical manifold whose fundamental group is the group I'm given. And let's say its minimal, its dimension is called M sub V. Well, in fact, there's a difference here with the closed case. So let me say M sub V is going to be the dimension of M sub V if the boundary of M sub V is not empty. And it's going to be the dimension of M sub V plus 1 if the boundary of M, if M sub V is closed. And then for a product of these manifolds, basically I'm either going to be using this or a closed manifold across a unit interval. I'm going to let the dimension of that, which will be basically the dimension of the product, more or less the dimension of the product of these M sub V's will be the sum of these M sub V's. So this is the dimension of the pieces.
Okay.
Yeah.
So for rags, you can describe a rag in terms of this finite graph, which just says which generators commute. I mean, can you say your results just in terms of that graph?
Well, I say it's the associated, it's the click complex associated to that graph. So that depends what the dimension of that is. So you take that graph and you fill in a simplex every time you see a complete graph.
Okay, I see. It's just.
And that might have some dimension. Okay. Like if your graph was, the one skeleton of a triangulation of a sphere, you'd end up with a triangulation of a two-dimensional complex.
I see. So then you get.
And D would be 2.
Okay.
And I need that for the geometric dimension. I mean, even if you think of a rag as being which I will, being a union of tori, the dimension of its k pi 1 has to do with the largest dimension of those tori, which are the simplices in this phi thing. It doesn't, you can't just get it from the 2 skeleton. I was hoping Cameron Gordon would show up. Actually, for Cameron Gordon proved this theorem for basically dimension 3. And for D equals 1. There's a theorem about 3 manifolds. Okay, so now what's the theorem for graph products? So the general result is that the action dimension of this graph product is less than or equal to the largest of these m sigmas. The largest dimension of one of these products. And maybe I should, and basically, if no MV is closed, then it's an equality. And the action dimension of each MV is the obstruction dimension. Some other little lie here. Then it's an equality. So the other case, we just have the general case, but the other case we can handle is if all these MVs are closed. So this is, the action dimension is still less than this, but in one case, if L embeds in a contractible complex of the same dimension, then the action dimension is actually can be decreased by 1. The action dimension of G is less than or equal to the same number minus 1. Okay. So now let me talk about the methods for proving this. Well, there's basically two things I want to discuss. So one is what you need to do to prove any theorems like this, or theorems for complexes of groups, is you need a way, a method of gluing to construct manifolds. If you have these pieces, you know, are given by, if you know the action dimension of the pieces of the G sigma, then you want to be able to glue them together. So that is the sort of method of Lay's thesis, which I want to discuss. And then that tells you basically what your guess is for the action dimension, and then you want to figure out how to actually find obstructors. So let me just say all I mean by gluing. So my only idea here, I'll write down when I need to do this, but I'm just, okay, so what I want to talk about is gluing and finding obstructors. So as far as gluing goes, the only way I know to get a manifold by gluing is to take manifolds of boundary and glue them together along an open subset of the open codimension 0 subset of the boundary. So glue together manifolds of boundary along a codimension 0 subset of the boundary. On the codimension 0 subset of the boundary. So the picture I have in mind, so suppose I somehow wanted to, glue together 3 surfaces. Instead of just making it 2 surfaces, I want to glue together 3 surfaces along some submanifold of the boundary. So the picture I have in mind is, maybe I'm just doing it along a single trivial fundamental group. I might have little intervals here, and so I just glue together these 3 surfaces by sticking on a little disc along these 3 edges. That's my basic picture. So what do I need to implement this for these manifold pieces that I'm going to be using for either the Artin group problem or the graph product problem? So what I'm going to need is, so I'm going to give him a system of some collection of manifolds. Usually, which I'll write n sub tau. Say tau is n is S of L. And the conditions, well, most of the time, except in these part twos, where most of the time I need the boundary of tau to be non-empty. Except sometimes for a vertex, I allow it to be empty. And if sigma is a maximal simplex, then I'm going to suppose that these all things have the same dimension. All maximal things have the same dimension for size n. And finally, there's this sort of, the codimensions have to go up by 2 every time. So this says that if you look at the codimension of one of these n sub taus in a bigger one, n sub sigma, well, if this was like a codimension 1 face, well, this has to be bigger than the codimension of tau in sigma, twice the codimension. The codimension, these things, each time you increase the dimension of the face by 1, you have to increase the dimension of the manifold by at least 2. So I'm thinking of these things as you know, n sub tau is this bg tau or something. Oh, I should have said, maybe I should have said, okay, 1.5 should have been that the boundary of n sub tau is contained in the boundary of n sub sigma, if tau is less than sigma. So each of these will be contained in the boundary of a higher dimension. Now, how do I glue these together? I have to talk a little bit about this thing here, which is what I call a dual disk, which is analogous to the dual cone.
Wait, what happens when the pieces have different dimensions?
These pieces, yeah, when the top dimension, then I just end up crossing the ones that are smaller dimensions with a disk to bring them all to the same dimension. Okay, right. No, that's a. Yeah, I might have to adjust by crossing the disk. Now, what's the idea of a dual disk? So this comes from, so I'm going to have to, these things have smaller dimensions, okay? The maximal ones are eventually supposed to all have the same dimensions. So we're going to have to cross this with something to make its dimension this. So what you do is, you look at the length of your simplex tau and your complex L. This is some complex of dimension, basically the codimension of tau minus 1, and you embed this in, so let's say let's say C of tau is this maximal codimension. This is codimension of tau in sigma, of n tau in sigma, where sigma is maximal. This is just, I don't know why I'm saying this. So you embed this in some sphere, but basically of dimension at least twice this, dimension C of t minus 1, which you can always do. Twice the dimension of the length plus 1. And then you thicken this up. I call the thick link, the thick version of tau, to be a regular neighborhood of the length in the sphere. And so and then the dual disk is basically a disk of this dimension, and it's got this thickened link contained in the boundary. So the picture I had in mind with those 3 points, for example, was that if my link of tau is just 3 points, okay, I would embed that in a circle, and I take a little regular neighborhood, which would be 3 intervals, and then I have a 2 disk with 3 intervals in the boundary, which is basically that picture I was drawing before. So now I do this. This might be regular neighborhood of a graph in the next higher dimension. And so now all I'm going to say about this is I glue together. There's some finer. These thick links are decomposed further, but basically I glue together this family. I cross these things with the dual disk to make them all have the right dimension. All have dimension n, and then I piece them together. And that gives me a manifold, and it's a thickening of this realization I was talking about before. Okay. Okay, I managed to start running out of time. So, now let me just say a couple things about obstructors. So actually, most of what, our ideas on this are based on what we did in the first paper with rags. So I want to, so the picture, the well-known picture for a rag, for if A is a rag, just reminding, then the well-known picture is this K pi 1 is this union of tori, one for each simplex in your S of L. And then its universal cover will be a union of universal covers of tori. So inside the universal cover, you'll have a copy of a union of Euclidean spaces. These are the lifts of these tori, all containing the same base point. These are called sheets or something. I'll just play the union with the same base point. Now what this looks like, so this is a union, this is a configuration of flats corresponding to this configuration of abelian subgroups. And in fact, it actually just looks like, in this case, this turns out to be the cone of the link of a vertex in dA. So this is a picture, for example, if you start out with, with say B with an interval, so BA is a torus, then you have sort of these two subtori. Now, L in this case would just be an interval, okay? Now the link of the vertex in these wedge of two circles is going to be the link of a vertex in one circle is just going to be a point, but the link of a vertex in two circles is going to be the link of a vertex in S1 is going to be an S0, not an S1. So in fact, you get the link of the vertex here is this square, it's this join. And so in fact, what we call this for some reason, we have this complex L, and we call OL to be sort of the boundary at infinity of this union of these R sigmas. And we think of this as just being given from the original complex. We call this the octahedralization. I could go into this for a long time, but I won't. The octahedralization of L. And what that means is you just replace each L by two vertices. Each vertex by two vertices, and then take joins. Now for the general Artin groups, what Yin and I did is we said there's a collection of free abelian subgroups indexed by a certain subdivision of L. So this is a subdivision of L which determines the sort of standard free abelian subgroups. And the idea is, well, if we took an Artin group on 3 generators, then corresponding to that we have this triangle, which then we do this doubling procedure to get an octahedron. Now, if we had something like the braid group on 4 strands, we have, I guess, free abelian subgroups of rank 3 in here. And the way you get them is, say, you take something in the center of this, which you think of the very center here. Say these two edges might be braid groups on 3 strands. You take their barycenters, and then you get some subdivision of the 2 simplex like that, and which corresponds to sort of the standard free abelian subgroups of the braid group of rank 4. So, but it's still a subdivision of L. So in this case, so what we proved in the first paper was that OL was an obstructor. And whether or not, if the topomology of L was non-zero. And so if the topomology of L is not zero, the topomology of the subdivision is not zero. So again, we get O of L subdivided as an obstructor. So the second thing was that the same process of doubling vertices, this subdivision is a D obstructor. Something obstructor is a 2D plus 1 obstructor if the topomology is not zero. Finally, I'm out of time, but let me just say in one minute, what you do with the graph products is you do some similar idea to get the obstructor. So the way we were picturing this, so for graph products, you're supposing that, I'm doing the case, the interesting case is when all these M sub V's are closed. As in the case with the right-angled Artin group, they're all circles. Now, in the right-angled Artin group, what we did is the picture we always draw is, just say over one simplex, you double one of these, you double each vertex, and then you take joins like that. You put in that, and you put in that. So you end up putting in this square for each edge, okay? Now, in this case of graph products, you say that the boundary of this M sub V is some sphere. In this case, the boundary was an S0, but in another case, it would be if it was a surface, it would be an S1. And what you do is you replace each of these vertices by a sphere of the appropriate dimension, and then you take the join of those spheres over this simplex. And that's what, and then you basically, it's a modification. You show that thing is an obstructor. Sort of a strange dimension. I think I should stop there.
intermediate, it turns out that the obstruction will be a joint of spheres.
In this last thing, yes.
Right?
Yeah, over each of these simplices, I'll have a join of spheres. So it'll be higher dimensional, it won't be. So in fact, it's a little strange what happens. This is, in these other cases, the obstruction dimension was basically twice the geometric dimension. But in this case, if this is a d-dimensional complex in there and say, forget m spheres, then this thing comes out to be something like an m maybe times d plus 1 dimensional complex, if all the spheres have the same dimension. Or it's something like m times d dimensional complex, and then there's another, this is m times d. So it won't. I mean, in the first case, it was d plus 1. Okay, maybe this is. In this case, it's going to be d plus m times d plus 1, and the obstructor. Now, what am I saying? I said, I'm going to keep writing this. The dimension of the complex is something like m times d plus 1, and then the obstructor doesn't lie in twice that dimension, it just lies in that dimension plus d. Okay? So, in fact, these are examples which are more like the mapping class grouper, that they don't embed in as large a possible dimension. They just embed in some lower thing.
But sometimes your estimate is sharp.
What?
Sometimes your estimate turns out to be sharp, right? You get the exact value of the action dimension.
We get we get that the abstraction dimension, we get an estimate of the abstraction dimension, and then we have an example of a manifold with the same dimension where it acts on. But even in in some cases, it's, even in the case of a right-angled Artin group, if you start with something where the simplices are d-dimensional, you have d plus 1 dimensional tori. So if you just start with a z to the d plus 1, its action dimension is d plus 1, which is not what we were talking about, 2d plus 1. And so it's not even sharp when you just glue together, two simplices. But once you start developing some homology, even in the link or something like that, then it becomes sharp.
Yeah, so not all contractible manifolds are simply connected at infinity, right? Not all of them are spheres. In fact, they're usually called Davis manifolds.
Yeah,
So,
right. That I was lying about that. So, we still don't know what to do. I'm still not sure. Right, I think we still don't know what to do when they're not spheres. I don't know, it's a question here. The question is it true that if you have one of these exotic contractible manifolds, is it always, does the cone on Sn minus 1 always coarsely embed in it? Is it coarsely equivalent to that? That might be the answer might be no, or it might be some question of Gromov or something like that. And I don't know that if it was, you might say, well, maybe you can replace these joins of spheres by joins of homology spheres or something like that. You're talking about where we're stuck right now. I think we're just going to end up finessing it. Assume that the boundaries are spheres.
Thank you. The same stuff.